children, you are joining with Guru Gedara educational program. Today I hope to start your science 15th unit, simple machines. Have you ever used simple machines? I know most of your answer is no. Let's look at these equipments. Hammer. We use hammer to fix the nails. And the door lock, you lock the door and unlock every day. And the scissor, you cut papers from your childhood. And screw nails, we use screw nails to fix two things together. And pulley, we draw water from wells using the pulley. What are these equipments? They are simple machines. You have probably used simple machines, but didn't realize that they actually called as simple machines. What simple machines do? They make our day-to-day work easier. Simple machines can be defined as tools which make our day-to-day work easier. By how? Simple machines make our work easier by two ways. Number one, by changing the magnitude of the force that we exerted to do a particular work. Number two, changing the direction that we exert the force. Now look at this diagram. This woman exerting a force to lift the box. The force exerted is less than the weight of the box. And it is easier to exert the force on the rod than lifting it using it with hands. Now let us look at the next one. The child is lifting a heavy weight by exerting the force downwards. It is much easier to exert a force downwards than lifting it upwards, exerting the force upwards. Okay. This way, the machines make our day-to-day work easier. Finally, simple machines collected together and form a compound machine. Every day, we are using these machines for various purposes. Simple machines can be divided into four groups: lever, inclined planes, pulley, wheel and axle. Today, I am basically focused about levers. What is a lever? Lever is a rigid bar which can turn around a fixed point called fulcrum. And levers are used to push, pull and lift objects. There are three important points of a lever. Fulcrum, it's the point at which the lever rotates. Load, the boulder to be lifted. Third, effort, the force used by the man to lift the boulder. Now you can say the effort is exerted on the rod and the load is lifted and the lever rotates around the fulcrum. Two important parts of the lever is load arm and effort arm. Effort arm, the part between effort and fulcrum is called as effort arm. The part between fulcrum and load is called as load arm. In the figure you can see fulcrum, load, load arm, effort, fulcrum. Earlier I told you a machine can increase the force that we exerted. How much a machine can increase the force? That can be calculated. That is called mechanical advantage. Mechanical advantage can be defined as number of times the machine increases the force that we exerted. It can be calculated using this equation. Mechanical advantage equals load divided by effort. Okay. Now, let us do a simple activity. There is a simple machine. Let us calculate the mechanical advantage of this machine. You can see the load to be lifted is 100 kilograms. Converted to Newton, 1000 Newton. The force applied is 50 kilogram, converted to Newton, 500 Newton. 1000 divided by 500, 2. Mechanical advantage of this machine is 2. Okay. Now, we did the activity and let us summarize that activity. The distance between the load and fulcrum. This point is act as the fulcrum. Distance between load and fulcrum is load arm, and distance between fulcrum and effort is effort arm. I measured the distance of the load arm, and that is 15 centimeters. And I measured the distance of effort arm, that is 30 centimeters. 15 centimeters, 30 centimeters. Look at this. Here is also another activity same to our one. This distance load arm and this distance effort arm. Here the load arm is lesser than the effort arm. Load arm less than the effort arm, and in this case mechanical advantage is greater than 1. Let us go to the previous activity. We got 2 for the mechanical advantage. In this activity, load arm is less than effort arm. So, now it is clear that load arm, when the load arm is less than the effort arm, the force exerted is less than the load. That means, effort is less than the load. Okay. Let us do another activity. Example 2. Here you can see the same weight, same load to be lifted by exerting a force, but the force or the effort we exerted is greater than earlier, that is 200 kilograms to 2000 Newton. Load is 1000 Newton, effort is 2000 Newton. Answer 0.5. Mechanical advantage is less than 1. Now, this is another different result. Now, let us do an activity related to this. This is a lever. This is the weight that we going to be lifted. It is load. Weight of the load is 4 Newton. This is the place where we exert the force, that is called effort. Through this point the lever rotates. So, this is the fulcrum. We use this we use this spring balance to measure the effort that we exerted. The distance between fulcrum and load is load arm. It is 20 centimeter. The distance between fulcrum and effort is 30 centimeter. 15 plus 15, 30 centimeter. Now, I exert the force using through this spring balance to lift the weight. and you can see the force exerted is 2 Newton, but the load is 4 Newton weight. Effort we used is less than the load, and you can see load arm is shorter than the effort arm. When the load arm is less than effort arm, the force exerted is less than the load. So, in that case, the mechanical advantage is less than 1. When the effort arm is greater than load arm, the effort that we exerted is less than the weight, and in such cases, mechanical advantage is greater than 1. Another activity, example 2. Here, the same boulder is lifting by exerting a force of 200 kilogram, and that is equal to 2000 Newton. Load is 1000 Newton. You know, mechanical advantage 1000 divided by 2000 is 0.5. Mechanical advantage is less than 1. Let us see what has happened. Here the load arm is greater than effort arm. Let us do an activity related to this. I use the same load to lift, and I change the place where we exert the force. Now the effort arm is 15 centimeter and load arm is 20 centimeter. I exert the force from this point to lift the weight. Now I exert the force through the spring balance and try to lift the weight. You can see much greater force has to be exerted to lift this weight this time. That is 4.5 Newton. It is greater than the weight of the load. So, when the effort arm is less than the load arm, the effort is greater than load. In this case, mechanical advantage is less than 1. When the load arm is greater than effort arm, mechanical advantage is less than 1. So, in this case, this is not advantageous. Practically, to increase the effort, we have to use a much greater effort arm than the load arm. In most of the simple machines, effort arm is greater than load arm to increase the mechanical advantage and to increase the force that we exerted. The levers can be divided into 3 types according to the position of fulcrum in relation to load and effort. Number 1, first order lever. In first order levers, fulcrum is in the middle of load and effort. Second order lever, load is in the middle of fulcrum and effort. Third order levers, effort is in between load and fulcrum. If you feel difficulty to remember, you just write flea and F in the first class order levers. In the first order levers, F is in the middle. That means fulcrum in the middle. In the second class levers, L is in the middle. That means load is in the middle. In third class levers, E is in the middle. That means effort in the middle. So, you can remember the order of the position of force, load and effort in all the three types of levers. First order lever, as I told you, effort arm is greater than load arm. To increase the mechanical advantage of this lever, and it is a force multiplier. That means mechanical advantage is greater than 1. But effort moves much greater distance than the load moves. Examples for first order levers. Scissor, effort, fulcrum and load. You can see fulcrum in the middle. Pliers, effort, fulcrum and load. Fulcrum is in the middle. And hammer, removing a nail, here is the fulcrum, load and effort. In all the three simple machines, fulcrum in the middle, in between load and effort, and load arm is less than effort arm. Here also effort arm is greater than the load arm. The second order levers. In the second order levers also, effort arm is greater than the load arm. Therefore, it is a force multiplier. Mechanical advantage is greater than 1. But here also force moves much longer distance than the load. Examples for second order levers: wheelbarrow, load is in the middle, effort is exerted by these points, and stapler machine, we all use stapler machines, this is the fulcrum, load, and here is the place we exert the force. Removing a lid of a fizzy drink bottle, force applied, load and fulcrum. A nutcracker, effort is exerted, here is the load in the middle of fulcrum and effort. Third order levers. In third order levers, it is little bit different. You can see fulcrum and load. The load arm is greater than effort arm, fulcrum and effort. Effort arm is smaller than load arm. So, in this case, it is a distance multiplier, because the load is moved much longer distance than the effort, but mechanical advantage is less than 1. That means, in third order levers, the effort is greater than the load. According to the activity we did earlier also, we proved that when the load arm is greater than the effort arm, the effort is greater than load. In third order levers, effort arm is shorter than load arm. Here is the fulcrum and load arm, fulcrum and effort arm. load arm is greater than the effort arm. In this case, the load should be lifted by a much greater force, because in here the effort arm is greater than load arm, but the load moves much longer distance than the effort moves. So, this third order lever is a distant multiplier, but the mechanical advantage is less than 1, as the effort is greater than load. Examples: broom. Here is the load, the dirty particles. We remove dirty particles by exerting the force in the middle of the broom. So, load moves longer distance than the effort. A tweezer, effort is exerting in the middle, load moves much greater distance than the effort. And in fishing rod also, effort is exerted by the middle and load moves much longer distance. In all the simple machines, effort is greater than load, but load moves much greater distance. So, simple machines, especially third order simple machines, are used as a distant multiplier. Velocity ratio. Another special factor that we have to discuss about simple machines is velocity ratio. In a third order levers, I told you it is a distant multiplier. That means the ratio between distance moved by the effort and distance moved by the load is called as velocity ratio. It can be defined as the ratio of the displacement of effort to the displacement of load during the same time. It can be calculated by displacement of effort divided by displacement of load. Now, let us do a simple calculation for velocity ratio. Here the displacement of effort is 3 meters. Displacement of load is 1 meter. 3 meter divided by 1 meter, 3. Velocity ratio of this machine is 3. That means the ratio between displacement of the effort and displacement of the load is 3. Okay, children. Now, let us do another important part of simple machines, that is work input and work output. We all know we have to exert a force to do a work by the simple machine. The force that we exerted to do the work on the machine is called work input. And after exerting a force, the machine do a particular work. That is called work output. In science, we calculate this work input and work output. Normally, work can be calculated force into displacement. In this way, work done on the machine or work input can be calculated by effort into displacement of the effort. Children, another important thing is the work done on the machine and work done by the machine. In normal life we do various works, but in science we calculate work in another different way, and it is little bit different from the normal life works. To calculate the work, the force exerted should be moved to a particular distance, and that is called as work. Work equals force into displacement. In calculating work done on the machine, we can use the effort and the distance moved by the effort. So, work input equals effort multiplied by displacement of the effort. Work done by the machine. When we exert a force and when we do the work on the machine do a work back, that is called work output. Work output can be calculated load into displacement of load. Now, let us do another calculation. In this simple machine, this load is lifted to a 15 centimeter height and the load is 9 Newton weight. The force that we exerted is 20 Newton and it moves over a 60 centimeter distance. Our equation, work input equals effort into displacement of effort. This is the effort 20 Newton and it is moved over 60 centimeter distance. Effort 20 Newton, displacement 60 centimeter, and normally when we calculating the displacement we should use meters. So, centimeters, I convert centimeters into meters by dividing 60 by 100. It is 12 joules. That means work input, work done on the machine by the man is 12 joules. Same way we can calculate work output. Work output means work done by the machine. What is the work done by the machine? The load is lifted to a 15 centimeter height. So, load is 60 Newton. A machine exert a force or machine do a work again backwards. That means, machine give out a work, that is called work output. Work input as well as work output can be calculated using this equation. First of all, let us look at this figure. Here you can see a first order lever and the force is exerted on the first order lever and force moved to a distance of 60 centimeter, and that is the work done. This is the force that exerted on the machine and the distance moved. So, by these two values we can calculate work input. Effort is 20 Newton, displacement moved by the effort is 60 centimeters, and you all know how to convert centimeters into meters. 60 centimeter divided by 100, because 1 meter equals 600, 1 meter equals 100 centimeters. The answer is 12 joules. What is this? Work done on the machine. Same way, let us calculate work output. Work output is the load magnified by displacement of the load. Here the load is 60 Newton and it is moved up to a 15 centimeter distance. So, how do we calculate the work done? Work done by the machine or work output, that is load into the displacement of the load. Displacement is 15 centimeter. Again you have to convert meters into centimeters. Work output can be calculated using load into displacement of load. Load is 60 Newton, displacement of the load is 15 centimeter. Load is raised to a 15 centimeter distance. 60 Newton multiplied by 15 centimeter. You all know 15 should be converted to meters, 15 centimeter should be converted to meters. And you will get the answer 9 joules. That is work done by the machine. Another important thing in the machine is efficiency of the machine. Efficiency means how the machine increases the force exerted to do the work. It can be calculated by this equation: work output divided by work input multiplied by 100. Why we multiplied it by 100? It is a percentage. You all know percentage, the percentage of the work given out from the machine for the work input is called efficiency. Earlier we calculated work output, that was 9 joules, and work input is 12 joules. As a percentage we will get 75%. You will think, why this machine can't increase its efficiency into 100? Why we can't increase the efficiency of this machine into 100%? Normally, practically, frictional force exerted, and due to that the efficiency cannot be increased up to 100. Now, let us find out another different way to calculate efficiency of the machine. I told you earlier, efficiency of the machine is work output divided by work input multiplied by 100%. This work input was calculated by load multiplied by displacement of load, and work input was calculated effort multiplied by displacement of effort. Look at this term, this is much familiar to you, load divided by effort. I think you could remember load divided by effort, that is equal to mechanical advantage, and displacement of load divided by displacement of effort. Think, you can't remember. Let us see. I separate this, load divided by effort, displacement of load divided by displacement of effort. As I told you earlier, load divided by effort is the mechanical advantage. Displacement of load divided by displacement of effort is not much familiar, but you studied displacement of effort divided by displacement of load. That was velocity ratio. This is opposite, upward, upside down. Displacement of all load divided by displacement of effort. It is 1 over velocity ratio. So, let us use these two familiar words in this equation. Instead of load over effort, mechanical advantage. Instead of displacement of effort divided by displacement of load divided by displacement of effort, 1 over velocity ratio. And our percentage mark, that also should be used. Finally, we got another different equation to calculate efficiency. Mechanical advantage divided by velocity ratio to 100. Now, I think you can remember two equations. One, efficiency can be calculated in the way of work output divided by work input into 100. In another way, efficiency can be calculated by mechanical advantage divided by velocity ratio into 100. So, children, remember the both equations can be used to calculate efficiency of the machine, but you should decide which one is used, which one should be used according to the given details. If you are given, when you are calculating the mechanical advantage, you have two ways. One is by using mechanical advantage and velocity ratio, and the other way by work input and work output. That should be decided by you. If you are given mechanical advantage and velocity ratio, you can use this equation. And if you are given work input and work output, you can use that equation. That should be decided by you. Okay, dear children. Now, let us do a question using all the factors that we discussed today's lesson. You are given a simple machine and you know what kind of simple machine is this now. Yes, it is a first order lever, and a 600 Newton load should be raised by exerting a 200 Newton force, and the weight is 600 Newton and it is raised to a 50 centimeter. Our first question, calculate the mechanical advantage. Yes, can you remember how to calculate the mechanical advantage? Yes, you write in a paper. And second question, find the velocity ratio of the given machine. Again, you remind how to calculate velocity ratio. Third question, calculate the efficiency of this machine. And finally, I ask you to find the work input and work output of the machine. Okay, children, now let us see the first one, mechanical advantage. The same figure I get to this slide also. As I told you, I think you can remember, mechanical advantage is load divided by effort. What is the load here? This 600 Newton. What is the effort? 200 Newton. Very easy. 600 divided by 200, that is 3 Newton. So, that is mechanical advantage. Children, can you remember what is mechanical advantage? Yes, that is the number of times this machine increase the effort exerted by the man. That means this machine increase 3 times the effort exerted by the man. Next, my question was velocity ratio, and I think you can remember velocity ratio is displacement of effort divided by displacement of load. Here, for the ease of calculation, I convert 2 meters to centimeter and 50 centimeters is the displacement of the load. Children, you also can use this kind of small tricks when you are doing your calculations. 200 divided by 50, that is 4. Velocity ratio is 4. Third question, efficiency of the machine. Can you remember I told you 3 ways of calculating the efficiency. Now, which one is suitable for this? Which is easier? We calculated mechanical advantage and velocity ratio. So, using this equation is much easier than calculating work input and work output. Can you remember? Mechanical advantage was 3 and velocity ratio was 4 multiplied by 100 because we are calculating a percentage. Finally, we got 75. 75 is the efficiency of this machine. Last one, work input. Remember what is work input? Work done on the machine, force exerted on the machine, displacement moved by the effort, that is 400. Finally, my last question is to calculate work output. To calculate the work output, you should multiply load and the displacement of load. This time I used the displacement in meters. There is a reason, because look at the last answer, that is expressed in joules. To get the answer in joules, we have to use the displacement in meters. So, children, very carefully you have to handle the units. So, finally, we got 300 joules for work output. Okay, children, today you studied many factors about simple machines. You studied what is a simple machine. It is a tool which make our day-to-day work easier. And how it make it easier? By changing the magnitude or by changing the direction. And then we discussed the main types of levers, as there are 4 types: lever, inclined plane, wheel and axle, and pulleys. Levers. Levers is a rigid rod which can rotate around a fulcrum, and we use levers to push, pull or lift things. And the 2 main parts of the lever as load arm and effort arm, and we did many activities using load arm and effort arm, and then we calculated mechanical advantage children, mechanical advantage is very important because it explains how simple machine or lever increase the force that exerted by the man, and you studied how effort arm and load arm affect on the mechanical advantage, and how effort arm increase and how to decrease the load arm, and how it going to be affected on mechanical advantage, such things. And then we discussed velocity, the 3 types of levers as first order, second order and third order. And then we discussed the examples for each type of lever. Okay children, now you have good knowledge about simple machines. I know at the beginning you didn't know anything about simple machines. Now I give you a simple activity. Go and find simple machines in your house. I think you can collect many of machines and classify them into 3 groups. What groups? First order levers, second order levers and third order levers. And you can submit it to your teacher. Another thing, during the lesson I told you, simple machines can be used to manufacture complex machines. And if you have any complex machine in your house, go and check and try to find 5 simple machines in that, and it also note down in your book and get corrected by your teacher. Okay children, this is the end of our first part of the simple machines. Hope to meet you in another amazing session about simple machines. Till then, goodbye.